So we're looking at page 17 in the Unit P packet. Here we're talking about graphically finding the solution to vector sums and scalar products. So we don't want it to be just as simple as adding the two components to one another. We want to do it graphically. All right, so it's kind of weird to think about it that way. And it's like, well, how do you do it graphically without taking into account any operations, mathematical operations, right? So there's two ways to find a sum of two vectors. One way is a parallelogram approach. So, and there's more ways, but two popular ways. So what I'm going to do is I'll show you the parallelogram approach, and then I'll show you what's known as the tail to tip approach. Both are pretty popular to the point where people tend to use them interchangeably, right? So what I'll be doing is taking vector u and translating it so that its tail goes to the tip of vector v, which is that point B. All right. Then I'm going to do the same thing with vector v. I'm going to take that vector and slide it up, translate it up, so that its tail goes to the tip of vector u. All right. And where they connect, that would give us a new point. All right. So that new point is going to be the endpoint of the sum of the two vectors. And we'll get into why that is the way it is. But for now, it's just a process. So that would be vector u plus v, the sum of the two vectors. All right. The other way of handling it would be kind of along the lines of what I was saying before, and that is, there's the two methods. One of them is the train of thought, parallelogram approach, and the other is the tail to tip approach. So if I were to take one vector and translate it so that its tail is at the tip of the other, and then create a new point at that location, connecting that with the origin, that would also give us vector u. Vector u plus v. All right. So basically, you get the same thing, except you're not connecting to make a parallelogram. All right. It's the same idea. There will be instances where we would want to have a parallelogram specifically, but that's particular to a type of question. All right. So when we want to figure out certain things like a scalar multiple or a sum of vectors, or maybe a combination of the two things, what we would want to do is use the information that's given. For example, in the case of the examples below, for example, that's fun. We have vector w. If I could draw, let me just bring that in, which looks like this for the most part. A little bit of variation is okay. If I want 3w, so question A is 3w, then all I would do is, using the same direction, I would just triple the length of that vector. All right. Vector u plus v, same idea. We need two vectors, each corresponding with the appropriate piece of the operation. So we have here, this is v. Pull that down. And this is my w. I prefer the parallelogram approach. I know physics people, it's kind of weird. Physics people like the tail to tip. Math people like parallelogram, for the most part. I mean, there are exceptions, of course. But if I'm finding the sum of the two vectors, I'm going to reproduce this vector, translate it over. I'm going to reproduce this vector, translate it over. and connect the two endpoints. And that new line segment, when made into a vector, would be the sum, v plus w. The tricky one would be part C, which is 2v plus, I'm sorry, 2v minus w, but it's going to become 2v plus negative w. All right. The reason why I say that is because, and it's an important distinction, negative, it changes the direction of the vector. All right. So we know v plus w has a certain look, but 2v, all right, so I'll take my 2v, so double this length. Now w would normally be heading in the downward direction, but it's a negative w, so it's going to go the other way. All right, so it's going to go, I kind of changed the size a little bit, so let me just make sure it's the right, it looks about right. So that would be negative w. So you change the orientation, so it's going in the reverse direction. So this would be 2v and negative w. Now if I want the sum of these two vectors, I'm going to use the parallelogram approach. Again, copy, translate, copy, translate. Give yourself two endpoints, the one where you started and the one opposite. Line segment connecting the two endpoints. And that would be 2v minus w. All right. So that's how you handle geometric cases. Right? So finding vector sums and scalar products and the combination of the two things using just a strictly geometric approach. So then now we get into the magnitude officially. Before I stole my thunder, now the thunder is back. All right, so it has been returned to myself by myself. So we have vector v is going to be equal to, if we're calling this a and calling this b, it's going to be the sum of the squares. So 36 plus 64, which is 100, under a radical, which is just going to be a 10. All right. So pretty simple. Now we could also think of those double absolutes. In essence, yeah, they're double absolute values to indicate magnitude, but at their heart, they are absolute values. All right. So when you take the square root of a number, it could be plus or minus. We're strictly going with the positive. So if I want, let me just make that. Oh, that looks terrible. If I want 5 times the magnitude of v, it's just 5 times that number, which is 50. As opposed to the magnitude of 5v. So let's figure out 5v first, which would be the scalar multiple of v. So let me just kind of smidge this over, tuck a 5 in there. I'll show the intermediate step. -6, -8. Which is -30, -40. All right, the magnitude of that 5v would be the sum of the squared values, so 900 plus 1600, which is 2500, all right, which is 50. All right, so we get out a new rule, all right, and that rule, now we haven't proved it, but we have demonstrated it, is that if you have some factor k multiplied by the magnitude of a vector, that's going to be the same as